Happy Monday. We are live. It would be amazing to see if how this live works out because turns out that my phone has broken. So I'm using my iPad to go live. So this is going to be a whole another world. Let's see what people think. Let's see what this live looks like. I do have a plan for the live, which is to hang out with Fuji Baji, and we are going to be speaking about astronomy, cosmology, and physics as usual while we hang out with the kitty cats and catch up with everybody. But we are live. I think it is working unless you say otherwise. I see the buttons and interface is a little bit different on the iPad that it is on my phone, so this is going to be an interesting experiment. I also wanted to say that happy February. It is still winter here in the Boston area, kind of snowing and raining sometimes here and there, precipitating and making it a bit colder or wetter, depending on which is happening. And I did hear that some people are actually getting sick, so sorry to hear that, and I hope you get well soon. And I saw a comment from my VIP guest on the live, Stephen, that he is not feeling so well right now. So sorry to hear about that, Stephen, and I hope you get well soon. Let's see how we do today here on the live. I do have my books ready and the topic ready, and I figured that today we will actually talk about a bit of a recap on the galaxy classification and the galaxy topic that we have been covering lately. So we have been speaking a lot about various types of galaxies in the universe and such. And the last time I went live, which was maybe a couple of days ago, I think I did do a live on Friday. So we covered quasars and we covered Seaford galaxies at that point. And we do have a little bit more left to cover under active galaxies. So that's going to be what we do today. Hello, welcome to the live. How are you? Welcome. Hello, good to see everybody. I don't know how the video. Hi, Gavin. Gavin Larimore says hi. Hello, Gavin. This is us. We're live. We're doing a kitty cat and astronomy live. Oh my gosh. Hello. Welcome, everybody. Welcome. Good to see you. Amnai says hi. Good night. Good night. Have a good night if you're if it's nighttime for you. Let me keep looking at your comments. Give me just 1 second because I'm getting used to this new interface actually for the live. So I believe that Anmai says hi, good night. Brad says please say happy birthday to Mike Hunt. Happy birthday to Mike Hunt. Hi, do you like 1 second. I'm so sorry. The chat messages are kind of disappearing. Hi, Mom Chill. Hi, Ignacio. Hi, DRD. Hi, Odds on Favorite. Gulabi ya Kali. Both. I like Gulabi as well as Kali. Very interesting. I don't want to be... Oh, hi, Mom Chill. Hi. Hi, Switching Teams. Hi, Gavin. Gavin Larimore says, shout out on me. Hello to Gavin. How are you doing? Hi, everybody. Thank you. If I interact with if I talk, go like this, maybe they will stay on longer. So my phone has broken, so I'm going live on the iPad. So excuse me if things are a little bit weird today. How tired are you? Well, I'm kind of tired, but this time I'm more curious about how the live will work on the iPad. Let's see. Okay. Mom Chill has some questions. I can't read the username here, but yeah. Shout out to Gavin. Thank you for being here. Thank you. Thank you for coming on the live. Thank you so much. Hopefully everything is still kind of working. Actually, give me 1 second. I'm gonna see what things look like on the computer, on the laptop, because that would be helpful for me. This is a new experience for me, going live on the iPad. So sorry about if the, you know, if the oh, thank you for liking the live. Actually, can people please like the like the live? Thank you. Oh my gosh, thank you for being here. Welcome. Thank you, thank you. Do I see more? Hi Lucas, how are you? How are you? How are you, Lucas? Okay, so you might hear the live come on my laptop. If you hear my voice twice, I hate offenders. That sounds like a good thing. Oh, you know what? You know what? I can see all the comments on my laptop, so I actually, it's totally fine if, so here's a fun fact. I usually go live on my phone and I can see all the comments and the live chats kind of appearing on the phone when the camera is rotated this way. But on the iPad, the messages are kind of disappearing. But now I have it up on my laptop. See, have it up, or maybe you can't see very easily. I have it up on my laptop, so you can actually see me and I can see your messages. So I'll be just fine looking at your messages over here. Okay, so thank you everybody for being here. Lucas says, hi, I'm fine, and you. Thank you so much, Lucas. Please do like the live. That would be amazing if you could like the live. And I'm going to cover the rest of the Active Galaxies portion that we were covering last time. So I don't know if you're new to this channel, if you're new to the live streams that I do, we cover astronomy, physics, and astrophysics and cosmology on the lives. And we also show the kitty cats. We also hang out with you. We also catch up with everybody that joins, especially if there is sort of a banter going on, or I know you already from a previous live session. So we kind of start with a chat, sort of hang out and casually talking and catching up with everyone. And then we continue with the topic. So that's what we're going to do today as well. And I see that some people have joined and left already, which is fine. People can come and go, and as usual, very thankful for you for being here. And also, if you see this as a video upload later on, I look forward already to your comments on the video, and hopefully I see many such comments. So leave us a comment if you're seeing this later on as a video upload. Thank you in advance. And if you're feeling sick, also get well soon. Okay. I see my own comments pop up now. So I'm actually gonna probably go like this so that I'm not on camera the whole time, because I'm actually just kind of trying this out, and it will help me to focus on the topic, which today we will talk about active galaxies. We have already covered Seyfert galaxies and quasars. We will continue that topic and talk about radio galaxies today. So you can kind of listen to this in the background like a podcast or audio file, if you will. And we will talk about the radio galaxies, and we will wrap up with some more comments on quasars and sort of a history of quasars. And that will wrap up the topic of galaxies. And I will also give you a little recap of what we have talked about already. So that's what's on the agenda today. I have been thinking also about talking about cosmology approach for galaxy formation. I'm still kind of preparing my notes on that. So basically, the fact that we have large scale structure formation, we have galaxies, this is sort of a development of certain anisotropies of the smooth universe. And there's a number of things that happened from when the universe got started, from the Big Bang. And on average, even though the universe is very smooth, there developed certain higher order perturbations and anisotropies. and those were different for different types of things, and those kind of ultimately led to these over densities in certain places, which ultimately then led to galaxies and stars and planets and all of that. And we, of course, are the life form that are supported on this planet Earth. And this planet Earth is, of course, a part of the solar system, which formed due to condensation of a giant gas cloud that was pretty rich in metals already. And those giant gas clouds actually come from stellar death, when a star dies and supernovas and puts all its material out into the interstellar medium. Sometimes these things will collect and form gas clouds or nebula, which then later on will cool down, condensate to form solar systems like ours. So that's sort of, I said the topic sort of forwards and backwards here. Hopefully that kind of helps to see where we are in the view, grand scheme of things. But in order to understand how the first sort of galaxies formed in the first place, coming from the Big Bang and onwards, is a very interesting topic. It's something that somebody actually asked about on one of these live sessions. So I do want to address it from a cosmological point of view, and I'm preparing some notes on that. So Big Bang nucleosynthesis. So remember, we've talked about the early universe. We've talked about how universe went from radiation dominated to matter dominated, and now it's dark energy dominated. We've also talked about cosmic inventory, cosmic ingredients, which are namely photons, baryons, neutrinos, dark matter, and dark energy. We've also talked about the Big Bang nucleosynthesis and how photons were king of jungle, and cosmic plasma was made of photons, electrons, positrons, and we had a bit of a break up with neutrinos at one point because of the expansion rate being higher than the rate of interactions between neutrinos and the cosmic plasma. So those are the sorts of things that we've kind of covered already. We've also spent some time on Einstein's equations and understanding some basics of general relativity. But actually there is a lot more to the story as the universe progresses and evolves to next do. Hi, I see somebody joined. Thank you so much for joining. Thank you for commenting. Thank you for liking the live. Please do like the live. So as the universe kind of continues to evolve and do more things and cools down further at the different temperature scales and larger just spatial scales too, there are sort of structures forming and overdensities happening. And there's a lot of math for all of that, which I'm still kind of deciding exactly how I want to cover this topic, how much of the math I want to include or not. But those perturbations and overdensities and the sort of anisotropies of the smooth universe that are different for different things is what ultimately gave us things like structure, and also the role that dark matter might play in forming these structures is also something that we've kind of mentioned, but we haven't delved into more deeply. So those sorts of things are going to be in the future. I wanted to give you a little bit of preview, but at this time we're still going to be on the topic of galaxies from an astronomy or astrophysical point of view, which is that, of course, we have a lot of galaxies, and they're all different types. And in order to get a good understanding of the astronomy of galaxies, we've been covering them in sort of an organized manner, I suppose, from this book called Foundations of Astrophysics by Barbara Redden and Bradley M. Peterson. So give me one moment. I will get started just in just a bit. I actually never shared my live. Let me do that. Reese, hello. My phone broke, Reese, so I'm using my laptop, or not laptop, my laptop to chat, and then I'm using my iPad to stream. Yep, I dropped it. I was using Google Maps while going somewhere, like walking, and dropped it on the street, almost lost it, and then somebody found it and I found it, but its screen is shattered and it doesn't quite work very well, and I've put it in a plastic bag, and because of it being in a plastic bag with the glass shards, I don't think it's very good for the live streaming. So it's indeed affecting my live streaming quite a bit, and I'm using this iPad. Hopefully you can hear me. Can you hear and see me okay? Oh, I just heard myself, so I think it works. I forgot to do an audio check earlier. I saw some people joined and I was talking to them and I kind of got distracted, so I'm not sure. Aww. Okay. Oh, thank you. Yeah, the screen has now shattered. What did you drop it? Shame you don't live here. Hi, Sundar. Hi, Reese. Hi, Crazy Paul. There's Baji. Right here. Do you see Baji? Baji's right there. Right there. Right there behind me. Where's my finger? There's my finger. Okay. Right above there. It's difficult to point on the iPad. The iPad camera is very different. Video is fine. Hi, Vasilisa. So Reese is here. Crazy Paul says hello. Crazy Paul, how are you? Sundar says hello. Vasilisa says something. I'm not sure exactly what it is, but thank you so much and welcome to the live. Reese says, yeah, I didn't see him up there. Hi everyone, please join us and chat. Okay, that was me. Okay, good. Hi Sundar, we're about to talk about active galaxies and continue that topic. Hopefully you're ready for that. So we will talk about radio galaxies today. Haha, okay. Okay. Hi, Gary. Gary says, hey, the cat lady. Yes, yes, indeed. This is me, the cat lady, right here. I remember asking you to show the shelves. Here you go. Here's 4 shelves. And there is Baji. There is Baji. Thank you. Thank you, thank you. Gary says, good to see you again. Thank you so much. There's the shelves. Suji is often climbing them. So, yes, that was me with the shelves. And this is Baji right here. He's kind of taking a nap right now. Because it is nap time. Thankfully, today the kitty cats are napping. I think they've had a lot of excitement. We had some friends come over and whatnot. So, are you remotely working? I mean, yes, pretty remote right here, right now. So, okay. Okay. Hello, everybody. Hello, everybody. Thank you so much for being here. Can you please like the live? Please like the live. And we will now get started. Yay, everybody. Thank you for being here. So we have talked extensively about galaxies. Thank you for liking the live. Especially we have talked about, I'll keep showing you Baji as well as half of my face, and we will also have the audio talking about galaxies right now. So thank you for being here. Thank you for liking the live. And let me just kind of recap for you what we have covered. So we know that about 100 years ago, when Hubble started to give us his excellent contributions from observing the universe, we got to know that there are actually other galaxies. Before that, it was not really known to us that there are not only other galaxies, but there are many, many other galaxies. So we live in the Milky Way galaxy, but the fact that when you look up at the night sky, many of the objects you're seeing that are bright and luminous are actually galaxies. This was not super duper known, and we didn't really have a clue about exactly how many, many, many other galaxies there were. So he started to observe these things and gave us actually even a way to classify other galaxies, and we've been kind of covering that here on the channel. So our galaxy, the Milky Way, is of course a spiral galaxy. It has a bunch of spiral arms. It has three main components, the disk, the bulge, and the halo. And we kind of talked about what these components mean and what sorts of things are in these components. And the fact that our galaxy is a pretty substantial spiral galaxy with a lot of things going on. It's not one of those galaxies that has no shape, and it's not one of those galaxies which has not a lot of things going on. It's a substantial, quite big galaxy. So that's the Milky Way galaxy. That's where we are. We are part of the Orion Spur, which is part of the Perseus arm of the Milky Way galaxy. Yes, so Reese has named some of the, I think he's trying to name some of the arms of the galaxy. Let me read to you, the names of these arms are kind of nice actually. Let me read to you some of these names of our arms. That will be part of the recap today. But basically, our galaxy, I think we should be pretty grateful for our galaxy because it's not a boring galaxy. I will say that. I'm trying to find the picture. So now also we Stephen, how are you? I saw that you were not feeling well. So sorry about that. Stephen is here. Reese is here. Gary says you are SA minor or major. Could you say again what that means? What is the URSA? I don't think I follow. Maybe if you could repeat your question, Gary. And then Stephen says, hey, Reese. Oh, very nice, Stephen. Please like the live. Thank you so much for being here. Galaxies. Okay. I'm still not following exactly what the question is, but let me tell you some of the names of the arms of our own galaxy. So we have the Scutum Centaurus arm, the Norma arm, the Sagittarius arm, the Perseus arm, and the outer arm. Those are some of the names of the arms of the spirals of our own galaxy. Oh, you are talking about some major and minor galaxies. Okay, I'm not familiar, but maybe it'll come to me as I continue the topic. Been feeling better, getting out of the hospital. Don't know when. My phone is dying, so I cannot stay long. Oh gosh. Well, hopefully you feel much better very soon and charge your phone. Thank you for being here, Stephen. Thank you for joining from the hospital. That is very dedicated of you towards astronomy. Aww. It's good to see you here. Aww. So our galaxy is a spiral galaxy. We've also talked about some other galaxy classifications, such as the elliptical galaxies, the irregular galaxies. Elliptical galaxies, of course, have the shape of an elliptical, an ellipse, and depending on the ellipticity of that galaxy, it can even be further classified. So we talked about that. Then we also have irregular galaxies, galaxies without much of a shape. And because we are classifying these galaxies morphologically according to Hubble, when it doesn't have much of a shape, we just call it an irregular galaxy. And within that topic, we also saw that how sometimes a galaxy is basically cannibalizing another galaxy, merging with another galaxy. And while this merging is sort of happening right now, or when we see it, it can basically look irregular. The shape can be kind of weird. We saw that some galaxies' shapes are basically plain weird. There was even a galaxy that we called the train wreck because of its shape, and it was basically due to galactic cannibalism. So we have covered these types of things in detail already. I wanted to recap for you sort of what we've been talking about. It's been a lot about these types of things like galaxy classification and what sorts of stars and what sorts of events happen in these galaxies. And then we went on to talk about active galaxies. Now, active galaxies are galaxies that generally will have an active galactic nucleus at the center, which will generally involve a supermassive black hole and jets of things coming out. But most importantly, the thing to keep in mind about an active galaxy classification is that its luminosity is coming mainly from that active galactic nucleus, or the luminosity of that AGN can rival the luminosities of all the other objects in the galaxy, including the stars. So even though we in our galaxy have a supermassive black hole which is accreting material, and that too is very bright, our galactic center is actually very bright in radio and X-rays, and we've talked about that as well. But we don't classify as an active galactic nucleus or an active galaxy because our luminosity from the stars and those types of other objects other than the supermassive black holes region is also very bright. We have substantial luminosity coming from the stars. So if an active galactic nucleus's luminosity can rival, compete with, or beat the luminosities taken together of everything else in the galaxy, then that's an active galaxy versus or a normal galaxy. So I had the flu since Tuesday. Oh gosh. You have the flu? Steven says I have flu A. I better go. Sorry. That's okay. This will get posted and you can always catch the rest of it later on, Steven. Hope you get well soon, Steven, says Reese. I had flu since Tuesday and collapsed. Oh my gosh. Oh my gosh. Get well soon, Stephen and Gary. So sorry to hear about the flu and all this. It is that season where people are getting really sick. Sorry about the flu. Oh my god, I can't even type. Yeah, don't worry about the live. Feel better, get well soon, and then you can always catch the rest of this later on. Crazy amount of congestion, but finally broke fever last night. Oh. Thank you for being here, even though you guys are sick. Appreciate your support. Appreciate your interests in these topics. Thank you so much. Okay, so now under active galaxies, like I was summarizing for you, we have further sort of classes to look at. So we have already talked about Seyfert galaxies, so we kind of did that already. And then we talked about quasars and how these were thought to be basically stars. Like we thought that they were very much looking like stars, quasi-stellar. Basically, quasar is a quasi-stellar, almost quasi-star. And it was interesting how quasars were discovered as basically quasi-stellar radio sources, but then turns out that radio quiet sources or quasars are also a thing. And in fact, because we discovered the radio loud ones, that is how we came to know about quasars and realized, oh my gosh, these are not stars, these are actually galaxies that are kind of different galaxies. And we looked at some examples of quasars at different distances, getting dimmer and dimmer and more pointy, of course, as you go farther away. But yeah, these radio quiet sources also are quasars when we discovered those, and the original radio loud quasars actually make up only 5% of the total population of quasars. So even though the more rare quasar is how we discovered quasars, but now we know about the radio quiet ones as well. So very interesting discovery happening here with the quasars. So we talked about that already in the last live. Now we will keep on going and talk about radio galaxies, and this is still going to be under active galaxies. So we're going to just kind of finish up active galaxies today, and we will touch upon a bit of cosmic history as well, and yeah, that will be that. And then we will sort of be done with the galaxies for the time being. And really, my interest is to talk about how galaxies formed in the first place in the universe as a large-scale structure formation topic, which some of you have even asked about. So that's the agenda. Thank you, Nausat. Thank you for liking the live, everybody. Thank you, Nausat. How are you? Nausat says, hi, how are you? Better part is it's about 50 here in New Jersey. Oh my gosh, yes, it's a little bit of a warmer day here in the north, isn't it? Now Sat says like down, thank you. Was able to sleep a near complete uninterrupted night last night. Oh my gosh, oh God. Keep sleeping, keep getting more rest. It is kind of warmer here, isn't it? And somehow we're sick. Somehow we're falling sick. I know a lot of people here too that are sick right now. Get well! Tea time. Feel better. Now, Seth, how are you doing? And please like the live. I think you said you did already, but just making sure. Okay, radio galaxies will be what we talk about now. Okay, so radio galaxies are defined simply enough as galaxies that have strong radio emission. So we mentioned about how the quasars, even though we saw the ones that were radio loud first, but actually turns out that there are many, many radio quiet quasars. Now we will talk about active galaxies that are actually very, very strong in radio emission. Sometimes the radio galaxies have a luminosity of radio emission that is over 10 to the 33 watts. So that's something to keep in mind. Which this 10 to the 33 watts is basically 3 times 10 to the 6th solar luminosities at radio wavelengths. So take the sun and times it by 1,000,000 into 3, and that's the type of radio emission luminosity we're getting from something like this radio galaxy. But as we, if we, this is sort of a number that we use basically to say that if the luminosity in radio, if we see a source, which is a galaxy that has a luminosity in radio emission over this 10 to the 33 watts number, then that's sort of a cutoff we might use. Because we are seeing galaxies with a lot of radio emission, so we have to figure out, okay, which ones do we call, which ones do we categorize as active galaxies that are radio galaxies? So anyway, if it's a spiral galaxy, for example, like ours, that's not got an active galactic nucleus where most of the luminosity comes from that, then that's another way, of course, that we would say that no, that's not an active galaxy if most of the luminosity is not coming from that active galactic nucleus. So the strongest radio galaxies that we know of have even more luminosity, something like 3 times 10 to the 11 solar luminosities. Strong radio sources are most frequency associated with elliptical galaxies. We talked about that the fact that morphologically elliptical galaxies is a classification of galaxies, but sometimes radio galaxies are classified as peculiar, as in the case of Centaurus A. So these are all the things to keep in mind. So sometimes an elliptical galaxy could basically be a radio galaxy because of very strong emission in radio. Or sometimes a radio galaxy is classified as peculiar because of some other, you know, reason. For example, probably some cannibalizing thing happening. We did talk about the galactic cannibalism actually. So, such as with Centaurus A. So we will look at this picture. Since I don't have my phone, pictures are going to be a little harder, but we will try to look at it. In a radio galaxy, the radio emission is not necessarily confined to a central nucleus. Extended radio galaxies have long jets that can be much larger than the image of the galaxy at visible wavelengths. So basically, it's not just about that what's happening at that galactic center, but also sort of what's happening around it. And in this case, we have these long jets that can be much larger than the image of the galaxy at visible wavelengths. So even though visibly you might not see these long jets, they're actually there, and maybe in this other wavelength, which is radio. For instance, Centaurus A is an extended radio galaxy, and there's a long radio jet of Centaurus A basically superimposes on its visible light image. And the jets of an extended radio galaxy can be over a megaparsec long. So we've talked about certain distances. A megaparsec is a very big distance, and these jets can have extension over that big of a distance. Pretty much the distance of, you know, that would be longer than many galaxies put together actually. But in this case, that's the extension of the jet. So quite remarkable. For reference, we are at 8 kiloparsecs distance from the galactic center in our own galaxy, and we're not close to the center. We're sort of off to the side. So a megaparsec is a very long distance. So you can see why we would classify such a galaxy as sort of a more special active galaxy, because it's doing this sort of long jet thing over a megaparsec distance, which is remarkable. Compact radio galaxies have smaller jets, frequently accompanied by an unresolved radio source at the galaxy's nucleus. Very long baseline interferometry reveals that the material in jets is moving outward at relativistic speeds. Indeed, the apparent motion of jets away from the nucleus often appears to be faster than the speed of light. Although this is simply a projection effect, of course, you know, there's no, you know, it's not actually superluminal. To find a compact radio galaxy, we need to go no farther than the nearby Virgo cluster of galaxies. So at one point, we actually mentioned the Virgo cluster, and in that Virgo cluster, we actually can find radio galaxy. The galaxy M87 is a bright elliptical galaxy near the cluster's center, goes under the alias of Virgo A, indicating that it's the highest flux radio source in the constellation of Virgo. So if you are a Virgo sun sign, maybe this would be interesting to you, that there is a bright elliptical galaxy near that cluster, and it goes under the alias of Virgo A, and it's a very highest flux, in fact, radio source in that constellation. In the central regions of M87, there's a 2 kiloparsec long jet seen at radio, visible, and X-ray wavelengths. So 2 kiloparsec, that's, you know, that is still a pretty okay number. As I was mentioning, our galactic center is 8 kiloparsecs away from where we are in the galaxy. So that is a length that I would associate for sure with a galaxy. But a megaparsec is a very long distance. So anyway, in the central regions of M87, so M87 is a galaxy, and towards its central regions, there's a 2 kiloparsec long jet seen at both, you know, all of these wavelengths, radio, visible, and X-rays. And Hubble Space Telescope imaging of the central regions reveals a gas disk perpendicular to the jet. So there's the jet, and then there's a gas disk that's perpendicular to the jet. And this looks like a sort of a mini spiral of hot gas in the center of our own galaxy, only an order of magnitude bigger. So we've talked about how our own galactic center is very bright in radio actually. So this so like I was saying, the 2 kiloparsec and the being visible in radio, visible in X-ray wavelengths, that's sounding more normal, like what happens sort of in our own galaxy as well, but it's a little bit bigger um, in scale. The radius of the central disk in M87 is 16 kiloparsecs. Oh, okay, I'm going home soon now. Okay, good. Congratulations on the hospital release. New flu virus. OMG. Congrats, Steven. Go home, take rest. Let me know later in the comments how you're feeling, and it would be nice to get an update. Thank you so much. Oh gosh. People getting the flu. So, putting those, speaking about those numbers again, the radius of the central disk in M87 is around 16 kiloparsecs, which you can compare again to our own distance from this from the galactic center. The sun and us, we're about 8 kiloparsecs away from the galactic center. So 16 kiloparsec long disk is not the most extraordinary thing. I mean, it is extraordinary, but it's still something relatable. We're seeing it at an inclination of 42 degrees. The observed spectrum of the disk reveals that it is rotating with a VC sin I of 460 kilometers per second, or a VC of 690 kilometers per second. So quite a bit of velocity there with the speed of the rotation. We can then calculate that the mass within 16 parsecs of the oh, wait a minute, I am reading this wrong. The radius of the central disk in M87 is 16 parsecs. I think I was reading it as kiloparsecs this whole time. Sorry about that. Wrong number there. I was reading this as 16 kiloparsecs and comparing it to our own distance of 8 kiloparsecs from the galactic center. But excuse me, M87's disk is 16 parsecs. That would make it kind of small. The radius of the central disk, let me read this again. The radius of the central disk in M87 is 16 parsecs, which is 4.9 times 10 to the 17 meters. We're seeing it at an inclination of 42 degrees. The observed spectrum of the disk reveals that it is rotating with VC sin I of 460 kilometers per second, or a VC of 690 kilometers per second. We can then calculate, like once you have your orbital speed, you can get what mass is within that radius. Remember, from Kepler's third law, we can then calculate the mass within 16 parsecs of the center as something like 2 times 10 to the 9 solar masses. Yes, that's Baji. Yes, you saw him. That's Baji over there. So the mass that's within the 16 parsecs of the center is 2 times 10 to the 9 solar masses. Oh wow. So there you go. That's the supermassive black hole at the center of M87, and it makes a lot of sense now, because the 16 parsec is of course very small compared to the kiloparsec that I was thinking it was. It wasn't. So within that 16 parsecs, we have this big mass of 2 times 10 to the 9 solar masses, which is the supermassive black hole at the center of M87. Sorry about the confusion. Hopefully I corrected all the numbers and you're good with it now. But now we have the supermassive black hole of M87 being 2 times 10 to the 9 solar masses, which comes from doing the math for utilizing the orbital speed, which we get from observed spectrum. Okay. Wow. Okay, great. M87, let me clip that. M87's supermassive black hole. All right, so accretion by supermassive black holes is something we will look at next. Um, Basically, we already kind of know from our prior discussions. For example, if you remember, for our own galactic center, we saw how we have a supermassive black hole. It's called Sagittarius A star at the center of our own galaxy, and it is the region around it is very bright in radio and X-rays as well, actually. And the brightness and the luminosity is really due to the accreting material that's falling into the black hole. So it's not that the black hole itself is bright, because black hole by definition is a massive compact object that has an escape speed of equal to the speed of light, right? So even light cannot escape. That's how we do the math and figure out things about a black hole, by solving Einstein's equations exactly for a black hole, putting the escape speed to be equal to the speed of light. A black hole is also sometimes called a dark star. It starts off as being a stellar remnant, or when a massive star dies, one of the options for it to leave a stellar remnant as is a black hole. The other options are white dwarf, neutron star, or black hole. Those are the three options, and depending on the initial mass of the star, generally it will either become a white dwarf or a neutron star or a black hole. But then a black hole is basically a very, very, very compact object. And if a very, very, very compact object kind of continues to accrete more material into it, continues to eat more material, then it gets more and more big. And so we think that supermassive black holes did not start off as supermassive, but they have become more massive as they accrete more material. And this accretion of material is why it ends up being such a bright source and gives itself away. So that's what we'll talk about. So as matter falls toward a black hole, a large amount of energy can in principle be extracted from it. So suppose a mass small m is falling from a large distance of r, much, much greater than r Schwarzschild. So we know that r Schwarzschild is the black hole radius, at which radius you cannot escape from the black hole anymore. Even light cannot escape. So, but say if you're at a large distance away and you're sort of falling towards the black hole, so now your distance r is much, much bigger than the black hole Schwarzschild radius. Well, then r Schwarzschild is, we know what r Schwarzschild is 2g m black hole over c squared. Its loss of gravitational potential energy will basically come down to something like a delta E, which is given by minus gm black hole small m over r plus gm black hole m over r Schwarzschild, which is around 1/2, which is going to be equal to 1/2 mc squared. Because basically when you have these quantities that are divided by the radius, if your small r, the distance from which you're falling into the black hole, is very big, then the quantity with that distance in the denominator will be small enough where you basically have delta E is equal to gm black hole times small m over r Schwarzschild, which is going to be equal to 1/2 mc squared. So that's the kinetic, because we can just put in the kinetic energy to be 1/2 mc squared, because it's the speed of light. So if the mass isn't halted before reaching the Schwarzschild radius, it will pass the event horizon with a speed of v equal to c over square root of 2, because we know that we get that from the Schwarzschild, and its kinetic energy will go to swell the mass of the black hole. So it's basically like, it's not gonna, if it doesn't stop, then it'll keep going and it'll end up in the black hole, making it more massive. So if the mass is decelerated by slamming into an accretion disk, which we can talk about, but it could do this instead, then its kinetic energy will be converted into thermal energy and then into photon energy. The conversion of gravitational potential energy into photon energy is not perfectly efficient. Some of the energy, for instance, goes into the kinetic energy of the outflowing jets. So this is all sort of doing an energy math. It is customary to write the energy carried away by photons as eta mc squared, where eta is a dimensionless number, sometimes called the efficiency of the black hole. It's how efficiently is the black hole sort of becoming more and more massive, if you will. And we expect this eta to be less than equal to 1/2. In practice, it is thought that a typical active galactic nucleus has an eta of around 0.1, which means that a single gram of matter falling toward the central black hole yields around 9 trillion joules of radiation energy. That is 9 trillion joules of radiation energy. As gas feeds into the black hole at a rate of m dot, the luminosity of the AGN is given by luminosity equal to eta m dot c squared. If we know an AGN's luminosity, we can then deduce its infall rate, m dot, which comes to around 0.018 solar mass per year. In general, we don't expect m dot to be constant with time, perhaps accounting for some of the variability detected in the luminosity of AGNs. The low luminosity of the galaxy's central black hole, which is 1,000 solar masses, implies either a low infall rate at the present moment or a low efficiency or both. So it could be low infall or low efficiency. So depending on the type of luminosity you're getting from an AGN, you would be able to determine whether it's just that right now the infall rate is low or whether it has a low efficiency, which would be given by that number eta. You might think that by shoveling in matter at higher and higher rates, you can make an AGN have arbitrarily high luminosity. In fact, there exists a maximum permissible luminosity for a given black hole of mass m black hole. Crank up the luminosity too high and the surrounding gas, or the gas surrounding the black hole, will be blown away by radiation pressure. So one might think that you can just make it more and more luminous by putting in more and more material, but at some point there's actually this limit coming from radiation pressure, because you would then be getting blown away and not falling in anymore. Consider an accreting black hole of mass m black hole and luminosity of the one we just mentioned, the eta m dot c squared, where eta is the efficiency rate of the black hole. And then we can assume that the black hole is surrounded by ionized hydrogen, because that's another thing we've seen as well, that the gas around the black hole can become ionized. At a distance r from the active nucleus, the photons have an energy flux of L over 4 pi r squared. So that's just luminosity divided by the area. In addition to an energy E, each photon has a momentum, remember, also given by small p, E over c. Thus, the outward flow of photons creates a momentum flux. So now we put everything in with what we just said, 1 over c L over 4 pi r squared, because E is the E over c, right? So we put in L over 4 pi r squared divided by 1 over c, times 1 over c. Because the photons carry momentum, they can exert a force on the free electrons and protons in the ionized hydrogen. So these photons, they carry a momentum, and as these photons are, so that's where this radiation pressure is coming from. When you have a ton of radiation, you will feel that, basically. You'll feel that thing. It's not just that a bunch of photons are coming out and nobody feels anything and everything is the same. No, actually you'll feel that. So they can exert a force on the free electrons and protons in the ionized hydrogen. The force exerted on each particle is the rate at which momentum is transferred to it. So as these photons come out, they transfer the momentum from themselves to the gas, And the rate of momentum transfer depends in turn on the particle's cross section for interaction with photons. Again, important thing to keep in mind: if you don't have if you whether or not you will meet somebody or collide with somebody depends on the cross section of that meeting or collision. Electrons have a much larger cross section for photon interactions than protons do. For instance, or for electrons, the relevant cross section is the Thomson cross section, which is given by 6.65 times 10 to the minus 29 meters squared. That's the cross section of electrons interacting with photons. So by the way, remember how in the cosmic plasma in the Big Bang we talked about the photons, electrons, and positrons being part of that cosmic jungle, interacting with each other, staying in equilibrium. This is the sort of thing that was happening even then. The electron experiences an outward force due to radiation pressure. The amplitude of the force is equal to the momentum flux times the electron's cross section. So, because what momentum are you giving to the electron depends on its cross section times that momentum to begin with. So all of that L over whatnot, that whole thing, L over 4 pi r squared over C times the sigma E, or the cross section of the electron. As the electron is accelerated, now it's accelerated because it's been hit by a bunch of photons that are coming out. It drags the nearest proton with it. Goodness, which maintains charge neutrality. Thus, so it's like hitting every hydrogen atom's electron, which then drags the proton with it. So every electron is now burdened with a massive proton that it drags along like a ball in a chain. There you go, ball and chain right there. The inward force on the electron-proton pair is provided by gravity. So it's being pushed away by the radiation pressure, but it's being also held, if you will. The inward force on the electron-proton pair is provided by gravity, which is the negative g m black hole mp over r squared y mp, because mp plus me, mass of electron, is much smaller than the mass of the proton. So this is what pulls the atom closer, but the radiation pressure is what pushes it outward. So the maximum possible luminosity for the accreting black hole is called the Eddington luminosity. So now we have two things. One is the radiation pressure given by what we just talked about, the luminosity over the 4 pi r squared over C times sigma E, which is the cross section of interaction between photons and electrons. Then we also have the F gravity, the force of gravity on this hydrogen atom, which is going to, in there, we will mainly consider the mass of the proton because it's much bigger than the mass of the electron. Then we can kind of set these two together equal to each other, because this is sort of the limit. You can't have just more and more luminosity, because as you have more and more luminosity, you also have more and more radiation pressure, and at some point those that radiation pressure will push you away, push the material away. And in this case, we're considering the material to be hydrogen atoms for simplicity, and the universe does mainly only have hydrogen as its most abundant element. So the maximum possible luminosity for the accreting black hole is called the Eddington luminosity. Sometimes we just say Eddington limit after the astronomer Arthur Eddington. The Eddington luminosity is the luminosity at which this outward radiation pressure, force, whatever you want to call it, exactly equals the inward gravitational force. So set those two to be equal, like I was saying. And basically, after you do that, the luminosity, or the Eddington luminosity, is something like 3.3 times 10 to the 12 solar luminosities times m black hole over 10 to the 8 solar luminosity. So you can solve this actually yourself and see if you get that or not as an exercise for you. The exact expression I just said is not so important. It's important to understand that those those things can be solved. Um, if the luminosity is greater than this Eddington limit, then the ionized gas will be accelerated outward and accretion will cease. The existence of a maximum luminosity leads to a maximum accretion rate for black holes. So if there's an Eddington limit, that means there's a maximum accretion rate, because after that you cannot be falling in anymore, you will be pushed out. And you get that here, maximum accretion rate. And if you try to feed a black hole more rapidly than this, it spews the gas back out. It is sometimes useful to express. So it's almost like the black hole too has a limit of how much it can feed and how fast. So it is sometimes useful to express this accretion rate in terms of the Eddington rate. And so we have m dot is equal to the big M dot over big M E dot, which we refer to as the Eddington ratio. But more than the dots and the math, if that's confusing, the important thing to remember is that don't just think about accretion, think about the radiation pressure of photons and how that can push the accreting material out and limit how much can fall in and how fast. So, wow. So this is why we talk about the luminosity as well. We talked about the luminosity typically and also the maximum luminosity. AGNs having a lot of luminosity will also mean that there is a lot of photons coming out, which also means that there is radiation pressure, which also means that there will be a limit to how much it can feed and how fast, because radiation pressure will push material outward. So isn't that so exciting? So it kind of keeps the black hole within a limit. Wow. Love that. So infalling gas does not plummet directly through the Schwarzschild radius and into the black hole. You could plummet directly into the black hole, but generally infalling gas will not plummet directly in. It will first do this pancake thing. So if the gas has any, so it depends on the situation, depends on what's going on. If the gas has any net angular momentum, it will first pancake into an accretion disk. So this is how we get accretion disks. We talked about how to plummet into a black hole. If you're trying to see the inside of it, then you would want to jump in a certain different geometry than if you wanted to die before you are reaching the inside of the black hole, because the black hole will put a lot of tidal forces on whatever is going towards it. If you're stretched out and spaghettified too much before you reach the event horizon, then you won't get to see what's inside. But speaking of these gases, depending on, again, angular momentum of the gases, there will be a sort of pancakeification. So depending if you're a gas, then your life is looks a little different near a black hole. There could be a sort of pancake forming instead, which contributes to the accretion disk. So if the accretion disk is geometrically thin but optically thick, so that each point on the disk's surface radiates like a black body, then the luminosity of that patch is basically we can get more math done now, saying that, oh, this luminosity is actually going to be a black body radiation. And so there's some more math that we can do and figure out what sort of accreting is happening around the black hole. Isn't that so interesting? The continuum emission from quasars typically peaks in the ultraviolet at an emitted wavelength of about 1000 angstroms. If this is the peak thermal emission from the accretion disk, Wien's law tells us that the temperature of the disk is about 3 times 10 to the 4 kelvins. And wow. And depending on where you're falling in from, you can figure out actually the ratio of that radius where you're falling in from over the R Schwarzschild. It's going to be around 14 times small m dot over eta to the 1/3. Eta, remember, is the efficiency rate at which the black hole eats, times capital M, that's the big M of the black hole, over 10 to the 8 solar masses, all to the minus 1/3. So these types of these types of mathematics are possible when you consider these different types of ways in which there is a limit, or there's a way in which it will accrete material. The energy that is radiated away ultimately comes from the gravitational potential energy of the patch, which can be written in the form of minus gm dnf over r, where m is the mass of the central black hole. As viscosity causes the patch to slowly spiral inward, it loses gravitational potential energy. So lots of cool things. So we're still covering active galaxies. We delved a little bit into the accretion disks of supermassive black holes. Of course, as you know, AGNs have the active galactic nucleus with this type of phenomena. So it's important to understand this. So I went into a little bit more detail than last time here. So, okay, moving on, let's talk about the structure of AGNs and unified models. Because so far we've talked about the Seyfert galaxies, the quasars, and now we talked about radio galaxies, right? Radio galaxies are simply just have a lot of emission in radio, significantly more emission in radio. And then we will finish with quasars over cosmic history. Yeah. Wow. How does the morphology of the narrow line region? I'm looking at the section here. Thank you once again. Oh, actually, you know what? Let's take a break and look at Baji. We can take a look at the K-Cats now with my iPad, which is kind of weird. Hi, Baji. Hi, Baji's taking a nap. It's not the best quality video today, guys, because of my phone breaking. It's just the iPad. But here is Baji. Oh my gosh. And here is Suji and Fuji. Oh my gosh. Oh, look at that. Oh. Okay, so we will continue. Let's see. Okay. Hello. All right. I'm sitting down and continuing. Hello, everybody. Thank you for being here. Welcome. So, hi, Ben. Hello. See you later. Bye. Oh, Stephen, hi. Are you back home? Please do like the live. Okay, so Seaford galaxies, BL-LAC objects, and radio galaxies seem to be something of a mixed bag with different morphologies and spectra. So we saw how Hubble had classified the galaxies based on shape or morphology, morphos, shape, Greek word, I think. So now when we have been talking about the active galaxies, we didn't really talk about shapes too much, other than these long jets that can come out of the active galactic nucleus. But that's because Seaford galaxies, the BL-LAC objects, and radio galaxies are sort of a mixed bag of shapes. Like, it's more about the activity that's happening within these galaxies that's of importance. And understanding sort of where the luminosity of these galaxies come from. Is it mainly coming from the active galactic nucleus? Is it mainly coming from the stars? In our case, we have a supermassive black hole that's accreting material, but we also have a lot of stars, and a lot of the luminosity contribution of our galaxy comes from our stars. So we don't classify as an active galaxy. Instead, we are a substantial spiral normal galaxy with a ton of spiral arms, a disk, bulge, halo, and all of that. So that's more of what we are as compared to these active galaxies. Stephen is saying, no, still in prison, aka hospital, waiting for the pardon, but I'm charging my phone now. Oh God, I'm glad you're charging your phone and you're still here and recovering from the flu. Is that handsome Baji back there? Yes, this is handsome Baji. I just went over and looked at him really quickly. He's doing okay. He's napping. So now, let's see what what the authors have to say about the structure of these AGNs. It's possible to describe all of the various types of AGN in the context of unified models. So we will see a little bit about what this means. I'm myself learning along with you. Unified models, the goal of unified models is to describe the broadest, love the teddy bears. Oh, thank you. Yes, the teddy bears are at this point the kitty cats, toys. They're my teddy bears actually from my own childhood, but yes. So unified models describe the broadest range of AGN phenomenology while using the fewest possible free parameters. So this is going to be some interesting stuff. We're gonna talk about the free parameters and fewest possible free parameters, leading to some description of these AGNs. The basic idea is that AGN structure is more flattened than spherical, and that the visibility or strength of various components depends strongly on the inclination of the AGN axis relative to the line of the sight. We start by listing the major components of AGN, starting from the inside and working outward. At the heart of every AGN, there is a supermassive black hole. So we know this, but always good to remember that we have a supermassive black hole at the heart of the AGN, doing all these activity, basically causing all of this activity. While this was suspected for many years, based on the combination of the energetics arguments outlined earlier and the observed rapid flux variability. So remember, there's a lot of variability in the flux with these active galaxies that we also consider to be part of the case about whether we call something an active galaxy or not. If there's not so much variability, then if things are more or less slow and steady, then it's a slightly different matter, because all of these jets and things that are happening, it's almost like the galaxy hasn't actually settled into a bit more of an active galaxy is almost something where it wouldn't be so stable and may not have grown yet to be more having all these more other features and stars and arms and things like we do. So we're lucky that we're not part of an active galaxy. We instead have been able to evolve, and gas clouds have been able to condensate and make solar system like ours and things like that. Uh, Aw, awesome. I see your comment, Stephen. So, in the case of AGN, of course, we have this active the supermassive black hole, and we suspected for a long time that that this might be the case, and the observed rapid flux variability implying a compact emitting region. This kind of told us too that there's probably a supermassive black hole doing and causing most of that flux variability, because number one, most of the flux is coming from that active galactic nucleus, and number two, it's very variable. If a galaxy has more than just an active galactic nucleus, then more things will contribute to its total luminosity, and it should not be so variable. It should be a little bit more steady as far as its flux. So having so much variability basically means, oh my gosh, there's this active galactic nucleus that's constantly sort of changing and doing things. So, but it's also about the recent spectroscopic evidence for supermassive black holes and AGNs, which comes in the form of the high-speed motions of stars and gas in galactic nuclei. So again, another thing is, if the stars and gas are moving at very high speeds, that also kind of tells you something. The Schwarzschild radius of a 10 to the 8 solar mass black hole is around 3 times 10 to the 11 meters, or 2 astronomical units. Surrounding the black hole is an accretion disk that accounts for the ultraviolet and visible continuum emission of AGNs. So the visible emission from a 10 to the 8 solar mass black hole arises on a scale of 10 to the 12 to 10 to the 13 meters. The origin of X-rays is less well understood, but they seem to be produced in a hot corona that surrounds the accretion disk. The jets observed in some objects are thought to arise on this same physical scale. Some ionized gas is ripped from the accretion disk by electromagnetic fields and spirals along magnetic field lines away from the disk, forming a jet. The accelerated electrons in the ionized gas emit, of course, synchrotron emission, accounting for the radio emission from the jet. So we talked about how electrons that are accelerated, sometimes they're accelerated relativistically, they will produce synchrotron emission. And this is another reason why the region can be very bright in a certain wavelength, could be radio, X-ray, whatever. But the synchrotron emission itself is what's causing that. Proceeding outward, the size of the broadline region is measured by timing the delay between flux variations of the ultraviolet and visible continuum. So it's almost like looking at the different types of wavelengths and seeing how to best describe it in the most simple manner. How to best describe the various sort of shenanigans that are happening in the AGN. Yes, having the jets is, yeah. We just talked about the radio galaxies, Stephen, and we said that they can have very long jets in the radio wavelength. Exactly. So when we proceed outward, we can see broadline region, the size of this broadline region, which is measured by timing the delay between flux variations of the ultraviolet and visible continuum and the response of the broad emission lines, a technique known as the reverberation mapping. So this is another, they're sort of trying to understand and parameterize the the active galactic nucleus. And this is called reverberation mapping, which is trying to measure the time delay of the, or sorry, the, yeah, time delay between flux variations of the ultraviolet versus the visible continuum. The time delay is simply due to the light travel time across the broadline region. The size of the broadline region scales with luminosity. It has been speculated that the broadline region may be the outer part of the accretion disk structure. The outer extent of the broadline region seems to be defined by the dust sublimation radius, the closest point to the continuum source where graphite grains can survive the intense ultraviolet radiation emitted by AGNs, dust at smaller radii where the equilibrium black body temperature exceeds 1500 kelvins, so quite a bit. Sagittarius A star is the supermassive black hole at our galactic center, and as far as our galaxy goes, we are not classified as an active galaxy because most of the luminosity in our galaxy does not come from Sagittarius A, it comes from our stars. So we do have an active, well, we have a pretty active galactic center, but we don't classify ourselves as an active galaxy because we have significant luminosity from other things that we are grateful to have. So, yeah. And the existence of dust is important as well in unified models because dust supplies a source of opacity that can block our direct view of the inner regions from some directions. The sublimation radius marks the inner edge of the dusty structure with a larger scale height than the inner regions. It is often referred to as the obscuring torus or dusty torus. All the evidence is, so dust too is something important. Although evidence accumulating that this region is not a donut-shaped structure, but it's rather the cool, dense part of a disk wind that arises from the accretion disk structure itself. So there's quite a bit more kind of talking about these different shapes and things, if you will, of the morphology. So the morphology. The inner part of the narrow line region is on about the same scale as the obscuring torus, but can extend out to hundreds of parsecs. The morphology of the narrow line region is often wedge-shaped or conical, and along the axis of the black hole accretion disk system. The narrow line region gas is apparently just the interstellar medium of the host galaxy. Interstellar gas that is not shielded from the central source by the obscuring torus is photoionized by the AGN ultraviolet radiation. So those are some things to consider when you want to sort of have a parametrized understanding of AGNs, because there is quite a bit of diversity and all kinds of different galaxies and shapes and morphologies of galaxies that can have these things. We're trying to see if there's a way to simplify our sort of model of it. So there's a little bit more on this, but I want to go on to the quasars over cosmic history topic, which will wrap up this section. So let's do that. Quasars over cosmic history, that's what we'll cover next. And I need to get some water and probably run to the bathroom real quick. So thank you so much for being here. Please do stay on. I will be right back. To stretch. Hello. See you soon. Fuji is wanting something. I see. I do see. Hi, Fuji. We are still here. 1 second. Just need to change their water, give them a snack, go to the bathroom, have a water myself. In fact, I might make some tea actually, because it is kind of cold and my throat kind of needs it. 1 second, please. Oh, there, their food has fallen. It did it automatically. Yay. I was always curious about quasars. Trust me, I've been confined to a small room for 2 days. I'm so excited to be getting out of here. Do not know when. Oh gosh. It'll be so bad. It'll be so good to go get back to your home. Let me know when you're back home. I need to stretch my legs so bad. Yeah. Oh yes, I need to stretch as well a little bit. Thank you for liking the live, everybody. Thank you so much. Really appreciate you. Okay, just need to put some water to be boiling and then use the bathroom. One second. Hi, Mark. Thank you. Thank you for being here. Hi, Mark. I like your cat tree. Yay, thank you. I have two. Aw, thank you so much for being here. Welcome to the live. We're taking a little bit of a break actually, but we will be finishing up with quasars and cosmic history just really soon here. I'm boiling some water. So hang tight. Hang tight. We will be right back. Hi, Fuji. Hi, Suji. 1 second, everybody. 1 second. 1 second. Alright, everybody, I'm back. Sorry about the wait. Harper, how are you? Long time no see. Not like I can go anywhere. I'm a captive audience waiting to get released from a hospital room. Harper! Just had a bad case of the flu. Was throwing up. Oh gosh. Yeah, people have been getting sick, not feeling well. For sure. That's really not good, guys. I'm so sorry to hear that. Harper, say something about how things are going with you. Steven has given his update, and hopefully he's gonna feel better soon. Baji. Okay. I'm glad your mom is here. I'm amazing. I just got another guinea pig on Friday. Oh, wow. Mom is here to drive me home. I was supposed to have had an ultrasound this morning. I got it done just an hour ago. Oh, so your ultrasound was late? Eating an apple. So next we'll talk about quasars over cosmic history. I used to love guinea pigs. Hi, Fuji. Fuji's sitting over there, looking at me. I'm amazing. I just got one. Real late, busy here at the hospital right now. Oh my gosh. Guinea pigs? Wow. Oh, you like turtles? Oh. Which kind? I like turtles too. It's like probably my favorite reptile. have two cats. Both are on my bed right now. Or next I'll eat the orange and then we'll start. That's cool. So we will talk about the quasar called 3C273, 2 billion light years away. I believe you've already heard about this quasar. Can anyone remember what we said about this quasar? I think Stephen might have been here at that time. May have. Ooh, and we're going to talk about something high redshift. Are you excited for Valentine's Day? Maybe. Excited? Maybe. Huh, I don't know. Babies. I've not been here a few days. Okay. You can see our discussion on the live tab. Oh, I love that. Okay. I wish I could show you some of the images too today. I think I will. Thank you. Thank you. That's kind. Baji, Fuji, and Suji. That's right. All right, let's get this portion done. Okay. So astronomers are fond of the saying a telescope is a time machine. As we look farther out in space, we are looking farther back in time. When we look at the quasar 3C273, 2 billion light years away, we are seeing it as it was 2 billion years ago. So if it's 2 billion light years away, we're seeing it as it was 2 billion years ago, because the light from that, which we see now, is reaching us at this time. So when we look at the quasar with the highest known redshift at z equal to 6.4, the relativistically correct equations tell us that we're looking at a quasar that is currently 27 billion light years away, and we are seeing it as it was 13 billion years ago. We know from the measured, so now let's read the footnote associated with this. The z equal to 6.4 quasar is currently more than 13 billion light years away because the distance between us and it has been constantly stretching during the past 13 billion years. So remember, about the expansion of the universe too, which is why it's farther away. So the universe has been constantly stretching during the past 13 billion years. At the time the quasar emitted the light that we see today, it was only 3.7 billion light years away. So the light that we're seeing it emit, the light that we're seeing now that it emitted, when it emitted that light, it was only 3.7 billion light years away. But so that's how we get these higher numbers. We know from the measured masses of black holes today that quasars must have relatively short lives. The most luminous quasars with luminosity of around 3 times 10 to the 14 solar luminosity must have accretion rates of around m dot of 200 solar masses per year to maintain that luminosity. The biggest supermassive black holes today have a mass of 4 times 10 to the 9 solar masses. To grow to that mass at the accretion rate of the most luminous quasars would take a time of around 20 mega years. Mega is 10 to the 6. If the most luminous quasars maintained their luminosity for the age of the universe, which is around 14 gigayears, which is the 14 billion years, they would have grown to around 3 times 10 to the 12 solar masses by the present day. When we compute the number density of quasars as a function of redshift, we find that there were many more quasars in the past than there are now. At the present moment, only 1 in a million bright galaxies is a quasar. So there used to be more quasars, actually, whereas now there are less. Let me turn this light on so I can see better. Hi, Fuji. Fuji doesn't like my... he didn't like that I gave him pets. Okay. So when we compute the number density of quasars as a function of redshift, we find that there were many more quasars in the past than there are now. At the present moment, only 1 in a million bright galaxies is a quasar. When the universe was about 20% of its present age, that is when it was around 2.7 gigayears old, about 1 in 1,000 bright galaxies was a quasar. Wow. So lots and lots more quasars back then when the universe was younger. Because remember, as the universe has evolved. There is, of course, so much more expansion, more dark energy, something we've talked about. Expanding things out. The black holes that accreted gas and drove the luminosity of the quasars haven't gone away. Black holes can only grow more massive with time. This means that the black holes that powered quasars are still around today, bigger and fatter than ever. They're just less luminous because they're being fed gas at a lower rate. Old quasars never die. They just go into hibernation when there's nothing to eat. One reason why supermassive black holes accreted gas more rapidly in the past is hinted at when you look at the high redshift galaxies that host quasars. Although some quasar hosts are fairly normal looking spiral and elliptical galaxies, most are peculiar looking galaxies in the process of merging. Galaxy mergers were more common in the past than they are now. So we spoke a lot about galaxy mergers as well, actually, in the last few lives. And remember how when galaxies merge, sometimes they make a peculiar shaped galaxy. Sometimes we call them plain weird, or one of them was called a train wreck, because then they don't really fit into any of the galaxy classification types based on shape anymore for at least some time, where the shapes were pretty much either spiral, elliptical, or irregular. And some irregular galaxies are basically these peculiar looking galaxies. But turns out there used to be more quasars in the past, and although some quasar hosts, there used to be more quasars, their black holes may have stopped eating, and so we don't have those jets that would make the galaxy be an active galactic nucleus, or the black hole be an active galactic nucleus hosted within an active galaxy. So it might have become more inactive over time, but those black holes are probably still around, bigger and fatter than ever. And even though some quasars are normal looking spiral or elliptical galaxies, but most of them are actually peculiar galaxies that are in the process of merging. The mergers may have not completely fully completed. For example, we talked about how we will merge with Andromeda after 6 billion years. We will be merged and part of an elliptical shaped galaxy. Galaxy mergers were more common in the past than they are now. In an expanding universe, galaxies were closer together in the past. So, as we know about the expansion of the universe making things farther apart, well, galaxy mergers would have been more common in the past because galaxies were more closer together in the past. When galaxies merge, their gas clouds collide, lose angular momentum, and fall to the center of the merged galaxy, where the black holes are ready to accrete them. So if that happened more often, then of course the black holes were being fed also more often, and accretion was happening more often, and active galactic nuclei were more common. When two galaxies, each with a central supermassive black hole, merge to form a new larger galaxy, it is not known with certainty how long it takes for their two black holes to become one. They may just form a stable black hole binary at the center of the new galaxy. So whether the black holes will merge completely or they will form a stable binary, and of course the binaries, when they rotate around each other, losing gravitational energy, would ultimately merge, but they could also just make a binary at the center of the new galaxy formed from the merging of the two galaxies. So yeah, really interesting how things have changed with cosmic history, with cosmic time. And so this is kind of like getting a little bit of a look at the cosmic history, which tells us about quasars in the past versus now. Bye, Harper. See you later. See you soon. Love it.